In Chapter 9, Section 3, we are going to be moving into talking a bit about some statistics. So the first thing we want to talk about is measures of central tendency, which is a very long way to say we're going to be talking about certain things that we've talked about, like averages, in a very specific way. So in this example, Sasha is an intern at Galois Incorporated and is interested in getting a career there. She is curious what her salary would be, and it's impossible to ask all 3,000 employees, so she asks 10 employees and gets the following responses. So in this, she got the responses of 45,000, 40,000, 55,000, 50,000, 50,000, 55,000, 60,000, 40,000, 40,000, and $640,000. Okay, so now how can we use that to talk about salaries at the company? Well, that's really the idea that we want to explore. So all of the employees at Galois Incorporated would be referred to as the population. The 10 employees that she asked are a sample of that population. We think of the individual responses as the values of a random variable. How do we distill a single measurement or statistic from this sample? All right. So one possibility would be the average or the mean. The sample mean is calculated by adding all of the values together and dividing by the number of values in the sample. So the symbol for the sample mean is x with a bar over the top, pronounced x bar. And if we added all of them up and divided by 10, we would get $107,500. Okay, so now that tells us that in her sample, the average salary is $107,500. Is that a very good representation of the salaries at Galois Incorporated? Well, that's a good question, and we want to know, right? If we just look at the 10 people she asked, how many people make more than $107,500 in her sample? Just one. 9 of the 10 people make less than that. In fact, 9 of the 10 people, or not even 9 of the 10, but what would it be? 8? 7 of the 10 make less than half of that amount. So there may be something a little misleading about that statistic. So the formula is often shortened using sigma notation, which is if we want to add up a whole bunch of things, instead of writing x1 plus x2 plus dot 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 all the way out to xn, we write it using sigma, the sum, as I goes from 1 to n of the x sub i's. All right, so talking about means, which is our technical word for averages, we can write that formula more succinctly using our sigma notation as follows. So a sample is a sequence of values of a random variable x. The process of collecting the values is called sampling x. The sample mean is the average of the values or scores in the sample. To compute the mean, we use the formula x bar equals the sum of the x's divided by n, or in sigma notation, the sum as I goes from 1 to n of x sub I divided by n. If the sample consists of all of the values of x from the entire population, we distinguish this by calling it the population mean, and we use the symbol mu instead of x bar. So the difference between x bar and mu is we use mu if we are averaging all of the people in the sample. So in the previous problem, that would be if we knew the salary of all 3,000 people at Galois Incorporated, we added all of those up and divided by 3,000, that would be mu. Whereas when we sampled only 10 of the 3,000 employees and found that average, we denote it as x bar. So mu is the population mean, x bar is the sample mean. All right. The next problem is for you guys. Given the set 4 8, 10, and 10, we want to find some sample means. So find the sample mean of all subsets of size 3, and then find the population mean. So just to clear up a little bit what we're talking about in question number 1, what would be all of the samples of, or subsets of size 3? Well, that would just be all of the ways we can arrange 4 objects 3 at a time. So our sets would be 4, 8, 10, 4, 8, 4, 8, 10, and then we would have 10, 8, 10, and 10, 4, 10. And I think that's going to be it, right? I don't think there's any other subsets of size 3. The 2, no. 4, 8, 10, 2 tens. Yep, that should be it. So go ahead and find the mean of those 3 sets, and then find the population mean. All right, so if we take a look at each of these, if we added up the first set, 4 plus 8 plus 10 over 3, that gives us 22 over 3, which is 7.3 repeating. The second set would be 10 plus 8 plus 10, which would give us 28 over 3, which is 9.3 repeating. The third set would be 10 plus 4 plus 10 over 3, which is 24 over 3, which is exactly 8. And then lastly, the population mean would be 4 plus 8 plus 10 plus 10, all over 4, which is 32 over 4, which is 8. So we look at this, and we see that our sample means, one of them happened to equal the population mean, but 2 of the 3 did not, right? So one of the things we're going to have to contend with is that if we are not sampling the entire population, that our sample means will not be equal to the population mean. So that statistic is only an approximation. So we can talk more about that idea of, well, when and how are those two things related? All right. So let's return to Sasha's quest for information on salaries. So we've got that table of values, and we had the average was 107,500, but it does not appear to be a very good representation of the data in the table. In fact, 6 of the 10 scores are less than half the average. So this leads to the idea, well, what are the shortfalls of the mean? So in this case, the mean does not seem to be a very good representation. So as this example is illustrating, so very large or very small scores can change the mean. So in this case, we have one score, 640,000, which is at least a magnitude, but many times greater than any of the other salaries. And that's what's causing the average to move up so much, right? So these outliers, or these very large, or on the opposite side, if they were very, very small, cause the mean to maybe not be the best representation of a data set. So when we're talking about measures of central tendency, we're going to talk about a few different ways to do it. So one of them is this, which is the arithmetic mean, or the sum, divided by the number of data points. So let's take a look at our next two measures of central tendency. So to overcome this shortfall, we will introduce two other means of central tendency. The median, which is the middle score, and the mode, which is the most frequent score. To find the median, we're going to have to sort the list into ascending or descending order. If the number of items in the list is odd, the median is the middle score. For example, if the list has n items, the median score is x sub n plus 1 divided by 2 item in the list. And if it has an even number of items, we average the middle two scores. So it would be xn over 2 and xn over 2 plus 1. To find the mode, we make a frequency table and find the value or values with the largest frequency. A set can have more than one mode if there is a set of data that has the same number of occurrences. All right, so let's find the median and the mode of this data set. So our 10 salaries. So to find our middle number, we need to rearrange this set into ascending order. So our smallest value is 40,000. And we have two of them. Three of them. I think that's all of those. And then we go to our next one, which is 45,000. Just one of those. Our next one is 50,000, and we have two of those. And we have 55,000, we have two of those. We have a 60,000, and then a 640,000. All right. So then we need to find the value in the middle. So essentially, just imagine chopping ones off equally from each side as we move towards the middle. We get to the middle two, and I added one too many zeros. That's not 500,000. It should just be 50,000. So we get here, and our median, it would be the average of these two. So 50,000 plus 50,000 divided by 2, which is going to be 50,000. So that's 100,000 divided by 2, which gives us 50,000. So now, to find the mode, we need to find the value that occurs most often. So we can make a frequency chart if we wanted to, but we can also just count. So how many 40,000s did we have? 3. And if we look at our 45,000s, we just have 1. And if we look at our 50,000s, we have 2. 55,000s, we also have 2. And each of the remaining ones, we only have 1. 1 and 1. So our biggest one is 3. So our mode is 40,000. Okay, so our two other measures of central tendency, the median and the mode, are 50,000 and 40,000. So let's talk a little bit about, well, what does the 50,000, what does the median represent? Well, we said it's the middle data value, but what does that mean? Well, it means that 50% of the 50% of the sample makes more than that value, and 50% of the sample makes less than that value. So when you have a sample of a population, it tells you, well, that's the middle point. Half of the people are above that, and the other half are below. So it tells you the upper half and the lower half. So while that's different than the mean that we found before, both of those are helpful. So in this situation, do you think that's a more accurate or a less accurate measure of the average salary at the company? Yeah, the median in this case would definitely be more accurate than the mean from the previous part. All right, so let's change our point of view. So in the examples so far, we have sampled the random variable x and tried to predict the value of the mean or other measures of central tendency. If we know the probability distribution of a random variable, can the mean be found without sampling? Well, that's a good question. So a fair die is rolled a large number of times. What do we expect the average of the numbers that are face up? Well, we'll use the table below for comparison later. So this was a data set that was obtained empirically by rolling a die 10 times, 100 times, 1,000 times, 10,000 times, 100,000 times, and 1,000,000 times. And based on what we see in that table, what number does the average seem to be getting close to? Well, it bounced around a bit, but it seems to be getting close to 3.5. So we'll make a comparison. So our goal then is, well, if we know the probability distribution, which we do for this, so if we make our probability table for rolling a die, so if we have x, and then the probability that x equals x, we have our outcomes are 1, 2, 3, 4, 5. That last box is a little skinny. 6. Well, if we have a fair die, what's the probability that we get any given number? Well, how many sides are on a die? 6. Yeah, so we get 1/6 for each of them. So then the value would be, well, we'd get 1s 1/6 of the time, we'd get 2 1/6 of the time, 3 1/6 of the time, 4 1/6 of the time, 5 1/6 of the time, and 6 1/6 of the time. So then, if we wanted to find the average value, it would be 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. So we already have a common denominator of 6, so it's going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 all over 6. So we add those up, and we get 21 divided by 6, which turns into, well, each of those are divisible by 3, so 7 over 2, which is exactly 3.5. So to find the average of this, what did we do? We took the value, which was x, and we multiplied it by what? By the probability that x, or a random variable, was equal to this. So really what we had was 1 times the probability that x equals 1, plus 2 times the probability that x equals 2, all the way out to 6 times the probability that x equals 6. So then writing this in a compact sigma notation, it would be the sum as I goes from 1 to 6 of, well, let's use n instead of I. The sum as n goes from 1 to 6 of n times the probability that x equals n. And so as we saw in the table above, if you rolled a die 1,000,000 times and took the average, it seems like it got pretty close to 3.5, right? Even at 100,000, it was pretty close. In fact, it kept bouncing just a little bit above and below after 10,000. It was a little above, then a little below, and then a little above as it was getting closer and closer to that value. All right, so what we just saw has a name. And that name is the expected value for a finite random variable. So if x is a finite random variable that takes on the values x1 through xn, then the expected value of x, written as e of x, or mu, which we used before for the population mean. So the population mean, or the expected value, as we just saw, is x1 times p of x equals x1 plus so forth in all of these, adding all of those up using the sum over all of these. So what does this really represent? Well, it's what does the expected value really mean? So if we think about it, let's go back to the previous example. So a fair die is rolled a large number of times. What do we expect the average of the numbers be that face up? Well, what this is telling us is if we repeat this experiment a whole bunch of times, we're going to get a whole bunch of 1s, a whole bunch of 6s, but the average of all of those values is going to approach what? 3.5, which really isn't even a number on the die, right? You can't roll a 3.5. But this just tells us that the average of all of those over a long time would converge to 3.5. So it turns out this idea of an expected value has many applications, as we'll see shortly. So what it really represents is the average, or what's going to happen in the long term. So this is what happens when we repeat an experiment a whole bunch of times. All right, so let's look at an interesting example. All right, so the rules of our game are as follows. We're going to roll a die. If you roll a 1 through a 5, you lose. If you roll a 6, you roll again. On the second roll, if you roll an odd number, you lose. And if you roll an even number, you win. The game costs $1 to play, and if you win, you get $10 plus your $1 bet back. So you make a profit of $10. And if you lose your dollar. So it costs you $1 to play a game. You roll a die. If you roll a 1 through 5, you lose automatically. If you roll a 6, you go to round 2. In round 2, you roll the die again. If you roll an odd number, you lose. And if you roll an even number, you win. So what is the expected value of this game? So in terms of this, what does that mean? If I play this game again and again and again and again, well, it's actually going to be more than that. We'll see. So let's go through and see what we get. So let's make a tree diagram to help us see what's happening. So in our first phase, we want to roll a 1, or we want to roll a 6, right? So if we roll a 6, we do that with a probability of 1 over 6. And then our other event is we roll a 1 through 5, right? And we can do that with a 5 out of 6 chance, right? There's one way to roll a 6. Everything else, 1 through 5, is a 5 in 6 chance. So if we get there, we lose, which we're done. Then in the second round, what happens? Yeah, we want to roll an even or an odd. So our possibilities are, if we roll an odd number, we're going to lose. So a 1, a 3, a 5, we lose. And so the probability of rolling a 1, a 3, of a 5, well, we have 6 choices and 3 outcomes, so that's 3 out of 6. The other option is we get an even number, which is 2, 4, or 6, which can also happen with a 3 out of 6 chance, right? And that's where we win. So if we lose, our outcome is we get negative $1, right? If we win, what's our outcome? We gain $10, so we get positive $10. And down here, we lose, we get negative $1. Well, we didn't gain that 1. We just get our dollar back. Because it was our dollar that we started with. So it's like if you bet $1, you get your dollar back plus 1, your net gain is 10. Right. Because the 1 was already yours. So now, what is our expected value? Well, the expected value of this is going to be our probabilities times our values. So our first branch going up is 1/6 times 3 over 6 gives us our probability of this branch is going to be 3 over 36. Going down this branch, we have 1/6 times 3/6. So that is also 3 over 36. And this branch is 5/6, which if we cared is actually 30 over 36, because then we can see 30 plus 3 plus 3 gives us 36. So that is indeed adding to 1. So our probability of winning is 3 over 36. Our probability of losing is 33 over 36. So now our expected value then, so our probability of losing is 3 over 36 plus 30 over 36, which is 33 over 36, which is 11 over 12. And our probability of winning is 3 over 36, which is going to be 1 out of 12. So then, let me move this guy down here. Our expected value is then going to be the probability that we win times its value. So we're going to have $10 times the probability that we win, which is 1 over 12, plus the value we get if we lose is negative $1 times our probability of losing, which is 11 over 12. So then that gives us 10 minus 11 over 12, or negative 1/12. All right, so our expected value is negative 1/12. Well, what does that mean? Well, let's grab a decimal for that fraction first off. So we have negative 1 divided by 12. So we get negative 0.083, repeating. So mu is negative 0.083, repeating. So what does that mean? Well, that's our expected value, or average. So what that means is that if we played this game a large number of times, so say 100 times, on average for each game, we would lose about 8 cents. You can't lose 8 cents in any given game, but over time, you're going to be losing more than you're winning, right? So if you lose 8 cents per play, on average, if you played 100 times, you would expect to lose about 80 cents. So the expected value tells us, well, what happens if you continuously play this game? So would you want to play this game with someone again and again and again and again? No. You might win a little bit and lose, but if you kept playing over time, on average, every game you lose 8 cents. So this is exactly how casinos make money. All of their games have a negative expected value. So while there are people who do win money, on average, that's why they just want people out there playing. That's why they give people free stuff to just show up. If you're, every time they pull, the slot machine handle, if they're losing, a tenth of a cent, or whatever the expected value is, that's why they want 10,000 people pulling it 10 times a minute, because those 1/10 of 1 cent on average add up. So over time, some people are winning prizes. That's great. They win money, but on average, everyone loses. This is the basic business premise of a casino. Make the expected value of all your games negative and you will win, because they're going for on average. They don't care if people win, some people win and some people lose. On average, everyone loses. That's the big idea. So based on that, we have the following definition. A gambling game with an expected value of 0 is said to be called a fair game, which means if you played that game again and again and again and again, your expected value is 0 means that if you played long enough, you wouldn't win anything and you wouldn't lose anything. So it's called fair, which means that your probability of winning is the same as your probability of losing in terms of prizes, which is what the expected value is. So a game with an expected value of 0 is called fair. The previous game is an example of what's called a bias game. The expected value is negative 1/12 or negative 8 cents, which means on average you lose 8 cents per play. So here are the results in some simulations of the game. I also have a spreadsheet that I made in Excel for you to play with if you want to play the game and simulate it a few times. So if you played 10 times, the average winning for 10 was 10 cents, so you were actually ahead. And then after 100, it went down to negative 0.12. After 1,000, it was negative 0.019. And then down to 2 cents, back up to 6 cents, and then it got close to 8 cents. So as we see, as people play, it moves up and down, but the more you play, the closer it starts getting to that actual expected value. So after 1 million plays, the average loss for those million plays was about 8 cents. That's the business plan of a casino. Somebody shows up and plays 10 times, maybe their expected value is positive. They won. But on average, when you average it over all of the people playing all of these, it always goes to the expected value, which means the casino makes money. So the expected value of a binomial random variable, is given by n times p, where n is the number of trials and p is the probability of success. So for a binomial random variable, we have a nice formula to help us figure out what the expected value is. So instead of having to go through that formula that we did above, if we know something is a sequence of independent Bernoulli trials, aka a binomial random variable, we can use this formula. So an exam has 20 multiple choice questions with 5 choices per question. If a student randomly guesses each question, how many correct answers can they expect to get? So in this case, we have 5 choices per question with 1 correct, so the probability of correct is going to be 1 out of 5, or 0.2. So that's going to be our p-value, so p is 0.2. And the number of trials, n, is going to be 20, because we have 20 multiple choice questions. So if the student randomly guesses on each question, how many can they expect to get correct? Well, our formula says that our expected value mu is n times p, so that's going to be 20 times 0.2, which is going to be 4. So if you randomly guess on a 20 question multiple choice test with 5 choices per question, if you just randomly picked answers, you would, on average, you would get 4 out of 20 correct. All right, example 5. So Sasha's back at it again. So she was able to get a frequency table for salaries from HR. Calculate the expected value. So she was able to get a frequency table, but it's for salary ranges. So for each of these, let's use the midpoint of each of these ranges. So the midpoint of 40,000 to 49,999 would technically be 89,999 divided by 2. But let's just fudge that a little bit and go 45, 55, 65, and so forth. So 45,000, 55,000, 65,000, 75,000, 85,000, 95,000, and then the last bin is bigger than the other ones. It goes from 100,000 to 1,000,000. So the midpoint of that would be $550,000. Okay, so we could add all of these up, but you may not remember from the introduction in this section that there are 3,000 employees. So each of these then, we could calculate our probability for each of these. This would be 973 over 3,000, 722 over 3,000, 551 over 3,000, 403 over 3,000, 299 over 3,000, 49 over 3,000, and 3 over 3,000. So now our expected value is going to be each of these times their probability. So in thousands, it's going to be 45 times 973 over 3,000 plus 55 times 722 over 3,000 plus 65 times 551 over 3,000 plus 75 times 403 over 3,000 plus 85 times 299 over 3,000 plus 95 times 49 over 3,000. And then this one is 550 times 3 over 3,000. Grabbing our calculator and getting to work on this. Let's see, we're going to have 45 times 973 over 3,000 plus 55 times 722. And I've already got a typo in that first one, so 3,000. 722 divided by 3,000. Alright, so that's the first two. Then we go plus 65 times 551 over 3,000 plus 75 times 403 over 3,000 plus 85 times 299 over 3,000 plus 95 times 49 over 3,000. And then lastly, plus 550 times 3 divided by 3,000. We get this value, and then this is in thousands, so times 1,000. So based on this, it looks like the expected value or mu would be $60,418.33. So it appears at Galois Incorporated that the average salary is around $60,418. So we can calculate population means by using the expected value. All right, so let's move into 9.4. So measures of dispersion. So looking at each histogram, the mean, median, and mode appear to be around the number 70 in each of these. The mode is different in each histogram. The central tendencies do not differentiate the data sets very well. From the histograms, we can see that the spread of the data is different. How could we make this idea of spread precise? So one idea is to look at the average distance from the mean. So that is, we could add up all of the data points and subtract off the mean. While the idea is sound, why would that always add up to 0? So the idea is if we wanted to talk about, well, how spread out the data is, why can't we just look at the distance from each data point to the mean? So each data point minus the mean would be the distance from the mean. Why, if we did that and added all of them up, why would we get 0? Well, let's try. So let's see what happens. If we write out the sum as I goes from 1 to n of x sub I minus x bar, well, that's going to be x1 minus x bar plus x2 minus x bar, adding all of those up till I get to xn minus x bar, right? So then we would have to divide all of that by n, because we're finding the average. So now let's regroup these. So how many x bars are there? Well, how many things did we add up? N, right? So how many of them there are going to be? Well, x1, x2, x3, x4, there's going to be n of them. So if we add x bar to itself n times, repeated addition is the same as multiplication. So there's going to be n x bars. So we're going to have n times x of them. So if we regroup these things as such, so x1, x2, xn, all of these things being over n, we would have x1 plus x2 plus dot, 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 all the way out to xn divided by n. All of the x bars are negative, so minus, and then we had n of these x bars, so n times x bar divided by n. Well, what is this first term? Well, what is x1 plus x2 plus dot, 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 xn over n? That's just our formula for the mean, right? And the mean is equal to x bar minus, and then I have n times x bar divided by n. Those cancel out, so I get x bar minus x bar, which gives me 0. So as good as the idea is of adding up and averaging the distance from the mean, it doesn't work. So how do we fix it? So our population variance and standard deviation. If the values x1 through xn are all the measures of the entire population, then the population variance is given by sigma squared equals x1 minus mu squared plus x2 minus mu squared plus dot, 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 all the way out to xn minus mu squared, all divided by n. So 1 over n, the sum of the differences of xi minus mu squared. And that is our population standard deviation is then sigma, which is the square root of sigma squared. The sample variance and the sample standard deviation, we have the same thing, but we use x bar instead of mu. And the major difference is, instead of dividing by n, when we're doing a sample, not the entire space, we divide by n minus 1 and not by n. So we get 1 over n minus 1 times the sum as I goes from 1 to n of x sub I minus x bar squared. Then the population standard deviation is equal to the square root of s squared. So the difference is if we're sampling the population and not doing the entire population, we divide by n minus 1 instead of n. So there's a lot of reasons for that. It's beyond the scope of this class for us to talk about why. If you take a statistics class, they will talk about it more. We'll just believe it's true. All right, so example. The following is a sample of incomes in the thousands of 8 U.S. residents selected at random. So 50,000, 40,000, 60,000, 20,000, 90,000, 10,000, 30,000, and 20,000. Calculate the sample mean and standard deviation rounded to one decimal place. What percentage of the scores fall within one standard deviation of the mean, and what percentage of the scores fall within 2 standard deviations of the mean? Okay, so we want to find the mean of these. So let's go ahead and use some technology to help us out. So getting our Excel spreadsheet. I think this is a different example. Indeed it is. First thing we're going to need to do is put our data into our spreadsheet. So in our first column, and I'll just label it data. We'll put in our values. So we have 50, we have 40, we have 60, we have 20, we have 90, we have 10. I'm sorry, what? Oh, the last two, 30 and 20. So Excel has some built-in functions that can do a lot of these things, but if we just wanted to, for instance, we could calculate the sum. So to do so, we would go sum, and if you want to add up all of the data in a column, you go A colon A, and that says find everything in A that is a number and add it up. So the sum of those values is 320. When we use that notation, notice that it ignores the table headers, so it doesn't try to add data. Because if you try to add a number, yeah, it ignores that. But if you, Excel gets mad if you try to add numbers and strings together, aka words, usually. But this will give us our sum. So sum. We get 320. So then our average, or our mean rather, would be our sum that we just calculated, so C2 divided by the number of data points, which is 8. So the mean of that set would be 40. Turns out that Excel has a nice formula for the mean. But they call it average. So you just go average, and you tell it once again we want to average all of the things in column A. And we do that, and we see we get the same thing.
And this is just a different way to use to find the mean, median, and stuff using Excel.
Yeah, so we can do it by hand, right? But if your data set has much more than 10 things in it, you're not going to really want to do it by hand.
And we can use Excel on the exam, so can we do it in a calculator?
You can use the data sets I'll make you use on any exams or anything will be something you can handle by hand.
Oh.
I'm not going to make you deal with giant data sets by hand. Anything like that would require Excel. All right, so now we want the average distance from our mean. So this would be our x minus x bar. And that would be the differences in these two things, right? So we take our data point, so that would be A2 minus E2. We copy and paste that down to give us the rest of these values. So paste. So that's our differences. So then we want the squares of all of those. So that's x minus x bar squared. So we would take this is equal to f2. We use the caret to say we want to square it. So 10 squared is 100. And if we did that with all of our values here, we paste again. And then finally, our last one is we want the sum of these again. So then the sum of all of those would be our variance. And this time we're summing our G column, so G colon G. And that gives us our sum, and then our standard deviation. Oh, we need to take this, and what did I forget? I added them up, but what do we have to divide by? The number of data points, right? So we're going to have to divide by, and in this example, is it 8 or 7? So what's our population? On U.S. residents, are there more than 8 people that live in the United States? So is this a population or a sample? We sampled 8 people, so that's a sample, right? So this isn't everything. So do we use, with our formula, is that we're not sampling the entire population, so what do we need to divide by? N minus 1. So our number of data points is 8, so what do we need to divide by? 8 minus 1, or 7. And then our standard deviation is going to be equal to the square root, which is in Excel, S is squirt. So we take the squirt of H2, and we get that our standard deviation is 46.59.
I'm still a little bit confused, but I think I'll just go to x.
Okay, so now we can also use built-in functions in Excel. So if you go standard std, you'll notice it pulls up 2 things. It has std ev, but then it's got .p and .s. So what do you think the P stands for? Population, and the S stands for sample, right? So if you go standard deviation S, then you go A to A, we've got to be more precise because it needs to know how many things. So we're going to have to go A2 through A9. And if we go the same thing but change our formula to P, you get this. So now we got to go figure out what I did, because apparently when we summed these up, we found the average of our things. So here, average of the squares of the distances. We found our mean. X bar A2, so these should be correct. We squared them. So hold on. We have our x minus x bars. Well, we needed the average of these, so I'm missing a column. Insert. So we need the average of these, of our x minus x bar. So this one was indeed our sum divided by 8. So sum of our g's. This one we have to divide by 8. Gives us our average of those. Formula is and this one, if we take the square root, something is not adding up here. Yeah, those are right. A2 minus here's our problem. A3 minus here's the problem. In my formula I forgot to lock my variable. So the mean wasn't moving. So it was, when I was going down, what it's doing is, notice it's trying to subtract E3. There's nothing in E3. So you have to use the dollar signs to lock your variable so that it uses that x bar, or you need to copy x bar all the way down. So if we do this, we'll get our values to turn out the way they're supposed to. There we go. And there we go. We get our standard deviations being correct. Okay. So once again, what had happened was, when I did this formula and copied down, you need to lock this variable so it's doing this, or the other option is you can just copy 40 all the way down and you'll get the same thing. So then we got our variance is this, our standard deviation was 26.18, same thing we got here, and if we assume it's the entire population, we end up with this. So there is a small difference between those two. In our question, I believe we were asked to round it to 1 decimal place. And then we want to know, well, what percentage of our data points fall within 1 standard deviation of the mean. So if our standard deviation is 26.18, our two values are going to be 40 minus our standard deviation, so I2, and 40 plus I2. So then what percentage of our data points are in between those two numbers? Well, let's see, 1, 2, 3, 4, not that one, not that one, 5, and 6. So we have 6 of our 8 data points are in this range. So 6 of the 8 are in that range. So right here, so 1, 2, 3, 4, 5, and 6. 6 and 8. 1 standard deviation of the mean. So as a percent, 6 divided by 8 is going to be 75%. Okay, 2 standard deviations is going to be if we take another 26 off each of those. So one more here, if we take 26, it's going to be about negative 13. You add 26 to this, 80, about 92-ish. And we'll notice with both of those values, in between these, that's 2 standard deviations. We pick up the last 2 values. In this case, it's 100%. So in this example, 100% of them are within 2 standard deviations of the mean. All right. So turns out there's a couple of rules that will help us out with that idea. So the first one is called Chebyshev's rule. So Chebyshev's rule says, for any data set and for k bigger than 2, the following pattern holds. At least 3/4 of the scores fall within 2 standard deviations of the mean. In our example, 100% did. But he says no matter what your data set is, that 3/4 of your data will always be within 2 standard deviations of the mean. 8/9 of your data will always be within 3 standard deviations of the mean. That's a typo. 3. And at least 1 minus 1 over k squared of all the scores fall within k standard deviations of the mean. So this formula works for any set of data. There is a specialized version of that formula for what are called bell-shaped curves. So a bell-shaped curve that is symmetric looks something like this. So if your curve seems to look like this, you may have heard them as the bell curve or the Gaussian distribution if you've taken a stats class. And you're probably familiar with this rule, which is 68% of the scores fall within that should be 1 standard deviation of the mean. 2 fall within 95%. 95% fall within 2 standard deviations of the mean. And 99.7 of the scores will fall within 3 standard deviations of the mean. So we can use these rules to infer information about statistics. So let's take a look at example number 2. The average lifespan of a battery is 9 years with a standard deviation of 2 years. Without any knowledge of the distribution of batteries, what can be said about the percentage of batteries lasting less than 3 years? So 1 standard deviation from the mean would be 9 minus 2 and 9 plus 2. So that would be the interval 7 to 11, right? So that's 1 standard deviation. 2 standard deviations would be 9 minus 2 times 2 and 9 plus 2 times 2. So that's 9 take away 4 is 5, and 9 plus 4 is 13. Well, we're still not there yet, so 3 standard deviations would be 9 minus 3 times 2 and 9 plus 3 times 2. So that's going to be 9 take away 6 is 3, and 9 plus 6 is 15. So finally, we've made it to this part where, all right, we know the average lifespan is 9 and the standard deviation is 2. So 3 years is 3 standard deviations away from the mean. So by Chebyshev, what do we know? Well, we can use this part right here. So we're going to have, here's our interval. So we're going to have 1 minus 1 over 3 squared, which would be 1 minus 1 over 9. So that is 8/9. Fall within 3 standard deviations. So then how much are outside of 3 standard deviations? So then 1/9 is outside. So with this, we can't say quite as much, because what's the least amount of time a battery can last? 0 years, right? If it's defective, it never worked. We're at 3 years is 3 standard deviations from the mean. 5 years was 2. 7 years was 1. 9 was our mean. But then we also have stuff on the other side, 11, 13, and 15. So what we know is that outside 3 standard deviations, so this part and this part, so this is 3 standard deviations, and this is 3 standard deviations, we know that 1/9 of the batteries fall there. We don't know if that 1/9 is more than 15 years, or we don't know if that 1/9 is between 0 and 3, right? Because 3 standard deviations from the mean goes in 2 directions. So what can we say then about the percentage of batteries lasting less than 3 years? So it is at most 1/9, which is, if we make turn our fraction into a decimal, we have 1 divided by 9. So as a percent, it is at most 11.1%, right? It's probably less than that, but we can't say because we don't know anything about the distribution. We know that this part right here plus this part right here in orange has to add up to 1/9. It could be all the defective batteries were between 0 and 3, and none of them last more than 15 years. But we don't know, right? So the best we can say is that it is at most 1/9, or 11.1%, will last less than 3 years. Okay, so now, if it is known that the distribution is symmetric and bell-shaped, now what can we say? Well, if it's symmetric and bell-shaped, we can use this part. So here's where we can use symmetry to help us out. So this is our mean, and then we have our standard deviations. So this is our 3 standard deviations, and this is our 3 standard deviations this way. But since our curve is now symmetric, so by symmetry, we know that A1 has to equal A2, as I have them labeled. So A1 has to equal A2, and 99.7% is how many fall within 3 standard deviations has to equal A1 plus A2. But if they're the same thing, that means that 2A1 has to equal, sorry, the complement of this. So that should be 0.03 or 0.3%. So A1 plus A2 has to equal 0.3%, but A1 and A2 have to be the same by symmetry. So 2A1 has to equal this. So we divide by 2, we divide by 2. So our A1 down here is 0.15%. So in this case, because of the symmetry, we know that less than, so that 0.15% less than 3 years. So knowing that something is symmetric and bell-shaped, we can use the symmetry because we know the things outside the standard deviation must be equal. So in other words, whatever that percent is, one of them is going to be half of that, right? Because if together they add to 0.3, then each of them separately have to be 0.15 because they're the same. And 0.15 plus 0.15 gives us the 0.3. All right, so let's take a look at our next one. Variance and standard deviation of a finite random variable. So if x is a finite random variable taking on the values x1 through xn, then the variance of x is sigma squared equals the expected value of x minus mu squared, which is x1 minus mu squared times the probability that x equals x1 plus dot 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 all the way out, or in sigma notation, xi minus mu squared times the probability that x equals xi. The standard deviation is the square root of sigma squared. So let's compute the variance and standard deviation for the following probability distribution. Okay, so we need to calculate all of these things. So the first thing we need to do is figure out some of these values. So I can't write as small as my table that I made, so let me snip it again and enlarge it. So I'm going to keep adding rows to this. So to use this formula, I need to know what these values are, right? So I have x, and I have the probability that x equals x in my table, but I need to know what x minus mu is. So the next thing I need to figure out is the average. So how do we find the average of a probability distribution? Right, but that's for a data set. For a probability distribution, it's the expected value, which is the sum of the xp of x's, right? So we need to calculate x times the probability that x is equal to x. So that's going to be, when we do this, we multiply them together. 10 times 0.2 gives us 2. 20 times 0.2 gives us 4. 0.3 times 30 gives us 9. 40 times 0.1 is 4. And 50 times 0.1 is 5. And 60 times 0.1 is 6. So then the expected value is actually the sum of all of those things, right? Or mu is 2 plus 4 is 6, 15, 19, 24, and 30. So now we need to keep computing this, so we need to know what x1 minus mu is. Well, we just calculated mu. Mu is 30, right? So we're going to do x sub I minus mu. So 10 minus 30 is negative 20. 20 minus 30 is negative 10. 30 minus 30 is 0. 40 minus 30 is 10. 50 minus 30 is 20. And 60 minus 30 is 30. So that's our x minus mu. But we don't need x minus mu. We need x minus mu squared. Right? So we're going to square each of these. So negative 20 squared is 400. Negative 10 squared is 100. 0 squared is 0. 10 squared is 100. 20 squared is 400. And 30 squared is 900. So now finally, we need to calculate the x sub i's minus mu times their probabilities. So that's going to be x sub I minus mu squared times the probability that x equals x sub I. So that's going to be this times our probabilities, which is row 2. So 0.2 times 400 gives us 80. 0.2 times 100 gives us 20. 0.3 times 0 gives us 0. 0.1 times 100 gives us 10. 0.1 times 400 gives us 40. And 0.1 times 900 gives us 90. So then sigma squared is the sum of all of these, is 80 plus 20 plus 0 plus 10 plus 40 plus 90, so 150 to 40. So then sigma is the square root of 240. Which gives us this value. So let's just kind of recap what we did. So we needed to calculate the x minus mu's, but before we could do that, we had to calculate mu. And mu is x times p of x, and then we add them all up, right? So we did that. We got 30. So our average, or our mean is 30. We calculated the x minus mu's, then we squared the x minus mu's, and then we took the x minus mu squared times the probability of each, added all of those up to get sigma squared, and then the square root of that is our sigma. So the variance and standard deviation of a binomial distribution or a binomial random variable, similar to the mean, has a very nice formula. That is, if x is a binomial random variable associated with n independent Bernoulli trials, each with the probability p of success, then the variance and standard deviation of x are given by sigma squared equals npq, and sigma is equal to the square root of npq, where q is equal to 1 minus p is the probability of failure. For values of p near 1/2 and large values of n, the binomial random value is bell-shaped and nearly symmetric. So the bell-shaped rule can be used when np is bigger than, n times p is greater than or equal to 10, and n times q is bigger than 10. So example 4, x is the number of tails that come up when a coin is tossed 3 times. Find the expected value, variance, and standard deviation. So what was our formula for the expected value for a binomial random variable? So that was from our previous section, right? So for a binomial random variable, we had that the expected value is n times p. So our coin is tossed 3 times, so that's n, and we want to know the number of tails that come up. So if we call our success a tail on a fair coin, that's going to be 1/2. So 3 times 1/2 gives us 3/2, or 1.5. So the expected value on a fair coin would be that we get 1.5 tails. That seems reasonable. So find the expected value, the variance, and the standard deviation. So the variance is going to be, well, n is still 3, p is 1/2, and q is going to be 1 minus 1/2, so it's also 1/2. So sigma squared is equal to npq, so 3 times 1/2 times 1/2 gives us 3/4. So then sigma is going to be the square root of 3/4, which is square root of 3 over 2. So square root of 3/4 gives us 0.866. So that would be our expected value, our variance, and our standard deviation. So for binomial random variables, we have nice formulas for each. All right. you've calculated that there is a 40% chance that a hit on your web page results in a fee paid to your company. Your page receives 25 hits per day. Let X be the number of hits that result in the fee, so successful hits. What is the expected value and standard deviation of X? Okay, so how are we going to resolve this?
By trying to figure out what N, P, and Q are.
Perfect. So we have calculated that there is a 40% chance that a hit on your web page results into a fee paid. So let's define that fee paid to be a success. So the probability of success is going to be 0.4. Then Q is going to be 1 minus 0.4. So the probability of failure is going to be 0.6. If our web page receives 25 hits per day, that would be our N. Let X be the number of hits that result in the payment of a fee. So what would be our expected value? So our expected value is going to be N times P. So 25 times 0.4 gives us 10. And so then what would our standard deviation be? So sigma squared is N times P times Q. So 25 times 0.4 times 0.6 times 0.6 gives us 6. So then the standard deviation is the square root of 6. Which gives us 2.449. So let's say about 2.45. Or better yet, let's just go to 2.5. All right, so part B says, complete the following. On approximately 95 out of 100 days, I will get between blank and blank successful hits. Well, we've been using a binomial distribution, and we know that it'll be bell-shaped and symmetric if what is true? N times P is bigger than 10, and N times Q is bigger than 10. So let's see, what is N times P is 25 times 0.4, which is exactly 10, so that's greater than or equal to 10. And N times Q is 25 times 0.6, which is 15, which is also bigger than or equal to 10. So since NP and NQ are greater than or equal to 10, the curve is symmetric and bell-shaped. So then our standard deviation is about 2.5. So then what is that going to tell us? So what's our expected value? Our expected value is 10, and our standard deviation is 2.5, right? So that gives us the intervals 10 minus 2.5, so 7.5 to 12.5, and then 2 standard deviations would be 5 to 15, 3 standard deviations would be 2.5 to 17.5. We actually don't need that many because what's our rule for the bell curve? To get 95%, how many standard deviations can we go? 2. So 95% will be within 2 standard deviations. So that's going to be this. So this is going to be our 95%. So to complete that statement, on 95 out of 100 days, I will get between how many? 5 and 15. Very good.